All right, so this is our last little lesson before we're going to have a review and then a quiz. The topic here is about relative velocity. So when we're comparing the velocity of, and we're going to do two main type of examples here, planes in windy conditions and also a boat on a river that's moving. So if we take a look at these three examples here, just so I can refer to them. The first, these are three different examples I kind of put in different places on the page. So on the first example here, it seems to me that this plane is moving south at 100 kilometers per hour, and the wind is also blowing now towards the south at 25 kilometers per hour. So just something about the wind. So when we talk about in English wind velocity, we would actually call this a north wind because it comes from the north and it blows towards the south. So make sure when you draw your diagrams, indicate which direction the wind is pushing somebody, right? So this is pushing the plane towards the south. So the resultant velocity is, well, if it was going 100 kilometers per hour without any wind, the 25 kilometers per hour are going to help it, and it's going to end up going 125 kilometers per hour. So the text here says the plane travels with a velocity relative to the ground, which is the vector sum of the plane's velocity relative to the air plus the wind velocity. So I think I'm just going to write a quick little note here about these three things. So for the first of all, the first one was about plane velocity. What do we mean by this phrase, plane velocity? So plane velocity is really the the velocity of the plane with respect or relative to the ground. Okay, so I'll put first of all relative. Actually, no, I should start off relative to the air. Okay, so if I'm saying in these questions that the plane is flying at 100 kilometers per hour, that means that compared to the air that's not moving around it, it's going 100 kilometers per hour. And sometimes we'll talk about, we can use the word heading to talk about the direction. And the speed, we'll often use the word airspeed. Here, let's see if I can get a little bit of space here. The airspeed will equal the speed. Okay, so when you're going 100, when I say that the plane has a plane velocity of 100 kilometers per hour, that means that if there was no air at all, there's no wind at all, I should say, if there's no wind at all, then it would also be going 100 kilometers per hour with respect to the ground. But because there is a wind, and the first question is going in the same direction, it adds together. So let's talk a little bit about wind here. So wind, and this is the important part here. If I'm talking about wind from the south, when you see something like from the south, you have to think about which direction it blows, okay? From the south blows to the north. Okay, so you would draw your vector north like that. This almost looks like north. Okay, so just be careful about which direction it is. If you're not sure, ask me. I'm not trying to be tricky. I just want you to be aware of how in English we talk about it. So in Winnipeg, for example, we get a cold north wind. So a north wind is actually blowing from the north and it pushes you to the south. All right. So my last one I should talk about is this resultant. Oops, I can't spell. Resultant. And it's the vector sum of these two things. So the plane velocity plus the wind velocity is the resultant, and that would be relative to the ground. And here, just like we have the word heading for the plane velocity, here we could talk about the word course. And so sometimes you see the phrase, I want you to chart a course. To chart a course would mean, well, given the fact that the winds might blow you off of where you're pointed. To chart a course means pick a heading so that after the wind affects you, you're actually going the speed and the direction that you want to be. Okay, so for example, if you get on a plane and you're going to Toronto, if there's a big tailwind, they'll tell you that you're going to get there a little bit earlier. They're doing this vector sum. Okay, the second example here is a headwind. So the plane velocity is 100 kilometers per hour, but the wind is going the opposite direction. You see the resultant. So it's pretty straightforward. Let's check out this last one here. They're at right angles. So the plane velocity is towards the south. The wind is blowing them to the negative x, or that would be the west direction, so this would be west. And you notice how they draw the two vectors and they get a resultant, okay? And they get a resultant of 103.1 kilometers per hour. And we will actually also be figuring about the direction as well, so we would calculate the direction counterclockwise from east on that one. Okay, so let's take a look at a few examples. Example number one is a plane is traveling at an airspeed of 455 kilometers per hour and is heading west. Okay, so why don't we use the same plane velocity? We'll use those same headings here. So we'll talk about, okay, we have a plane velocity plus the wind is going to give us the resultant. And remember that these are vectors. They're not scalars, so we're not going to just add them normally. We're going to add them like vectors. So the first one is an airspeed of 455 kilometers per hour. That's exactly what we want, so we'll put a 455 kilometers per hour west in there. Plus, if a wind from the south, so again, I see this from the south, and if you want to think about this, you can say, okay, if it's going from the south, okay, so here's south over there. If it's going from the south, then it's actually blowing this way, isn't it? It's blowing you to the north. So you actually want to put in there 95 kilometers per hour north. Okay, now our resultant is going to be equal to, we don't know. We're going to figure that out. So when we draw these arrows, I like to draw the east-west ones first. So the fact that it comes first in our equation is fine, but we're going to draw the west one first. So say, okay, we're going west 455. And now we're going north 95. So we're going to get a resultant. And I'll try to do this in a nice dashed line here. There's a resultant, and our resultant has direction if it starts here and ends there, so this would be the direction of our resultant. Okay, so we want to figure that out. So my r here, I'll use r for resultant in this case. R is going to be equal to, using Pythagoras, the square root of 455 squared plus 95 squared, and I think I get a number of somewhere around 465. Now I should also figure out the direction. So if I think about, here is my resultant, I think about where the resultant is starting and going away from there. So I'm going to draw my east, west, north, south grid here. I'm going to figure out this theta inside that triangle. So I have the opposite side and I have the adjacent side. So often I end up using tan. So it's going to be the inverse tan of 95 over 455, and when I punch that into my calculator, I get something like 11.8 degrees. Now I should still convert that into counterclockwise from east. So when I'm thinking about that, it's going to go like this, right? And so my direction will actually be 180 minus that, right? So 180 degrees minus 11.8 degrees will equal 168.2 degrees. So I end up with an answer of 465 kilometers per hour at 168.2 degrees. Actually, sometimes I like having that 11.8. This is how I would write that. I could also write 465 kilometers per hour at 11.8 degrees north of west, because it gives me a good sense of where it is. So both of those are just they're good ways of answering it. You don't have to do both. You can do either way. Okay, so there's example number 1. I hope that makes sense. Let's take a look at number 2. Now, the pilot from the same plane from example 1 realizes, she took this physics class, and she realizes she's going to be blown off course. What if, okay, going back to the diagram, if she's starting here and she's going to get blown off that way, she's going to end up somewhere further north than where she wanted to be. Okay, and just a little worried about what this would look like if you were on the ground watching this, right? So I cannot draw an airplane, so let's pretend that this little arrow is an airplane. The airplane's actually going to be pointed, straight west, but the direction that it's traveling will be this way. So as you see, the airplane is going to be kind of, be slipping to the sideways while it's moving forward across the sky because the wind is blowing it. So even though it's pointed straight west, it actually moves 11.8 degrees north of west. Okay, so how could the pilot compensate for that to actually get straight west? All right, so, well, let's start off by answering the question, using the same method that we had just a second ago. And we'll say now that the plane velocity plus some wind is going to give us the resultant. What's different about this question is that we know something about the resultant. We want the resultant not to be this one at the angle. We want the resultant to be straight west. So I'm going to start off by drawing the resultant. So I'm going to say, okay, I want this resultant to end up looking like dot, 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 or, straight west like this. I'll draw it a little bit longer so I got more space to write things. So that's how I want my resultant. I don't know what the speed will be, so some speed we don't know but I know it's going to be straight west. Okay, now the wind, I know it's the same wind, and the wind was 95 kilometers per hour north. So I don't know exactly which way I'm going to be heading yet, but I know the wind is going to be pushing me north. So I have to think, okay, if the wind is going to be pushing me north, I'm going to add this vector like this. Here is the way that I'm going to have to point the airplane. This one will be the heading, so that when the wind pushes me north, my resultant is actually straight west. Right? So here is my wind. That's the 95. And then this is the plane velocity. Now for the plane velocity, it's still going to be 455 kilometers per hour. It'll still have that airspeed, but the direction is the one I don't know. Okay, so the two parts that I don't know is I don't know, okay, this is 455. I don't know this direction. Okay, and I don't know the amount of this resultant. So you see these two question marks. Now, are they actually asking? They say, which direction will she have to point her plane so that she ends up due west? So really what I need to do is find out what's this direction here. Okay, so it's this theta that I need to know, and I'll use that theta afterwards. So inside this triangle, I know I got to be careful because normally I know what the resultant is. Or sorry, normally I know what the two sides are. This time I know the resultant. So this is the opposite side, and this is the hypotenuse. So that's where you use sine. So the sine of the angle is equal to the opposite side, which is 95, divided by the hypotenuse, which is 455. So theta will be the inverse sine of that, 95 over 455. And that angle will be, I did it somewhere, I just have to check, 12 degrees, pretty close to 12 degrees. Okay, so now thinking about how to state that 12 degrees. So here is my north, south, east, west grid. So this is my 12 degrees here. My counterclockwise from east, now I'll have to add 180 to that. 180 degrees plus 12 degrees is equal to 192 degrees. So my answer is just 192 degrees, right? Or I could say 12 degrees south of west. Oh, that would be fine. I didn't do so well. 12 degrees south of west. Okay, so you notice that the questions ask which direction it is, right? So people have a tendency of trying to find they really want to find the side there, right? But we don't need to know that side. We just need it was only asked what direction, okay? Um, that side would be um, what would that be? How quickly they would be going west, right? So we know she's going to go west afterwards, and this side here would be the resultant ground speed, how quickly she would be going west. But we were asked which direction she needs to point her airplane, which is a different question. Okay, so we're going to turn over to analysis of a riverboat motion, which is actually quite similar. So here's a diagram that I stole once again from physicsclassroom.com, and it's a motion of a motorboat with current. So this light blue area is the water, is the river, and the river is moving towards the north, and the boat is heading straight to the east. So you hear this is pointed east, and you get a sense of what I was trying to draw with the airplane, and I didn't do so well. So the boat is pushing towards, pointed towards the east, but because there's the river, it actually, slips downstream while it's moving across. Okay. Now we're supposed to find out the resultant velocity. So we're going to say the same thing that we said before. We're going to say that the boat velocity, and this boat velocity, this is the velocity of the boat relative to the water. Okay, just like before, we had plane velocity, and that was the velocity of the plane relative to the air. This is the boat velocity relative to the water that's in. And then the current is very similar to the wind, right? So the current is the velocity of the water relative to the shore. And those two added together are going to get our resultant, which would be the boat velocity relative to the shore. So if someone was watching that boat move from the shore, they would see it take that path, right? Okay, so in this question we have 4 meters per second is the boat. Is that what it was? Yeah, 4 meters per second east, and then the river is 3 meters per second north. Okay, so we can draw a diagram. So we got, 4 here, and then we have plus 3, and I think you're going to see it, or I think you're anticipating my resultant is going to be 5, right? Because we know that 3, 4, 5 Pythagorean triple, but we also need to find the direction here. So the direction theta is going to be equal to the inverse tan of opposite over hypotenuse, or sorry, opposite over adjacent, which is 3 over 4, pardon me, which is 37 degrees. And since it's in the first quadrant, right, it's 37 degrees, that's our answer. So the question was asking the resultant velocity. What's the resultant velocity? And the answer would be 5 meters per second at 37 degrees. Okay, so that's your basic question. There are a couple other questions that you're often asked. So we did A, we said what is the resultant velocity, and then there is if the width of the river is so many meters wide, how much time does it take for the boat to travel across the shore? And also, what distance downstream does the boat reach the opposite shore? So how far downstream did it end up, right? So if it was pointed for straight here, but it ends up over there, how far downstream did it end? So how far down the shore did it work? So we're going to be using this average speed equation. This is slightly different than we usually write it. I usually write it like V is equal to delta D over delta T. Okay, now in the MOP questions that you're going to be doing, he asks quite a few questions, and he does quite a few conceptual things in this. I'm going to show you a pretty quick way to answer these three types of questions. So example 1 is the same question. Part A is the same question. So I'm just going to redo our diagram real quick, and I'm going to put this is 4 here, and it was 4 meters per second, and then we had 3 meters per second, and then we had this resultant over here, and that was 5 meters per second, and here was 37 degrees. Okay, now this you'll note is what kind of vectors. These are velocity vectors, right? So I'm just going to put velocity up here. The answer for A we already have was 5 meters per second at 37 degrees. Now B says if the width of the river is 80 meters wide, how much time does it take the boat to travel shore to shore? Now the hint that they gave us already is that we're going to be using this V is equal to delta D over delta T. Okay, so if the width is 80 meters wide, in other words, the distance from here to here, this is 80 meters. So this is the distance, that's the displacement I should say, that the boat is going to be taking. So you'll notice one thing right away. This is a velocity diagram and there's no 80 meters on it. So what I'm going to do is draw another diagram, and this is going to be a displacement diagram. So this boat will be traveling at that same, I'm going to draw, it's going to be a similar triangle. There we go. So this is the direction that it'll be traveling. Similar triangles, the corresponding angles are the same. It's still going to be going at 37 degrees, right? And it's because that's the direction that it's moving. So after some period of time, it'll have moved in that direction. And I know that it's going to be 80 meters here. And so what's neat about this is that we can see this similar triangle relationship here. If it is moving 4 meters per second in the direction straight across, like I know it's moving 5 meters per second in that direction, but these are the two components of its motion. So how quickly is it moving across the river? It's moving across the river at 4 meters per second. How far is it in that direction? Okay, so the rule is you have to use the direction from the velocity triangle and the same direction in the displacement triangle. Okay, you can't take the 5 and then the 80. You got to use the 4 and the 80. Okay, so let's use our V. So we're doing part B. Let's use our V is equal to delta D over delta T, but let's use the same corresponding sides. Okay, so if they're moving at 4 meters per second, how long does it take them to go 80 meters? Well, first of all, let's redraw this, rearrange this formula to solve for delta T. So I'm going to multiply both sides by delta T. V times delta T is equal to delta D, and then from the next step I'll divide both sides by V. So finally I will get delta T is equal to delta D divided by V. Okay, or if you can think of this it's sort of like cross multiplying, where you can switch these two, so you see the V and the delta T switched. Okay, it's amazing how often people make a mistake in this. The delta T, they get the V on the top and the delta D on the bottom, so be a little bit careful on that. Alright, so in the delta D that I'm going to use is the 80, and the velocity I'm going to use is the 4, so 80 divided by 4 is 20. And this is the neat thing too, is that if you get meters divided by meters per second, right, dividing by a fraction is the same thing as multiplying by the reciprocal. So I'm going to say, oh, instead of dividing by meters per second, I'm going to multiply by the reciprocal, which is seconds per meter. And then you can see the meters cancel each other out and I get seconds. Okay, or you can trust the formula, its time is 20 seconds. Okay, and you can also say, oh, like just the triangles. 4 times what gives me 80? Like in the sense that the sides are proportional in similar triangles. 4 times 20 gives me 80. So very, very quickly you can say, well, what are the other lengths? This side, 3 times 20, this one would be 60. Right? 5 times 20, this would be 100. Okay. Now what questions would those answer? This is my answer for B. And now looking at C, it says, what distance downstream? What distance downstream? Now that is this 60. Okay, that is how far downstream it went, would be the 60. Now if you weren't comfortable just doing the similar triangles type of solution, here you can say C. Again, what distance downstream? It'll be this version of the formula. We'll say delta D is the distance downstream multiplied by how quickly it was moving in that direction multiplied by how much time. So if the downstream one, let's pretend we don't know what the 60 is. This is this direction of the displacement, right? Because this is down the stream. And this is how quickly they were moving downstream. It's the current. So if the current is 3 times 20 is going to be equal to 60 meters. And there is our answer. Okay, example number 2. And then I think there's a U-turn coming up because I've been talking for a while. This should be your turn pretty soon. Motorboat's traveling 4 meters per second east and encounters a current traveling 7 meters per second north. It's the same question. All that we've done is we've taken this 3 here and we've changed it for this 7. So I'll do, first of all, what's the resultant velocity? Okay, so I'll just do a very quick velocity diagram here. So we have a 4, and now we have a 7. Looks like this. And here is my resultant. Okay, so using Pythagoras on that one, I need to check it out. Using Pythagoras, I would get 8.06 meters per second at, and it would be again the inverse tan of 7 over 4, 60.3 degrees. Okay, so that's the answer to A, just very quickly because I want to speed things up a little bit. And then it says B, if the width of the river is 80 meters wide. So again, I'll do a displacement diagram, and this side is 80. This side, I don't know. Like that. Okay, but I do know that these two triangles are similar because this angle is going to be equal to this angle, and we have 90 degrees here. So how many seconds does it take to get across? It's the exact same value, isn't it? Still 20 seconds. So that's interesting. If you have a boat that can go 4 meters per second, and if you point it straight across the river, it doesn't matter how fast the current is. The current doesn't make any difference. That's if I'm going straight across, right? It takes me 20 seconds to get across, so that's my answer for B. And then C is what distance downstream does it take? So in other words, what's this value over here? So I'll put an X over there. So what's X equal to? So again, we can say, well, the direction it's going, it's 7 meters per second. It's going for 20 seconds. So delta D in that direction is going to be equal to whatever the velocity is in that direction multiplied by the time. So it's 7 times 20. So it's going to go 140 meters. So what changed when we sort of turned up the current on that one? Instead of ending up 60 meters downstream, it took the same amount of time to get across, but we ended up getting further downstream, 140 meters. Okay, I'm going to stop now and give you time for your turn, and then I'll finish it in another video. Thanks.